Hello everyone. Today in this video we will continue the topic which we left in our previous video, that is the capacitance of a double circuit line or capacitance of a parallel circuit line. In this video we will see the configuration in which conductors are in vertical spacing and or flat spacing. In previous video we saw the conductors were on the vertices of a regular hexagon. Now let's see how to derive. Here I have shown a double circuit line with phase conductor A, B, C, A dash, B dash, C dash. Now as you have already seen that conductors are so placed that there is maximum possible spacing between the same phase conductors. That is why A and A dash, C and C dash are placed diametrically opposite. Now as you see that this spacing is different for every conductor, so we need to transpose this line so that we can somehow get some symmetry. So we will transpose this line and we will see that in section 2 phase A conductor will come at position 2 here and phase B conductor will come at position 3 here. Similarly phase C conductor will go from position 3 to 1, that is shown here. Accordingly, this part will change: C, C dash, B, B dash, A dash. Similarly, now this A will go to this position, B will go to this position and C will come to second position, and accordingly this side will change. Now let's see how to write the expression for the potential difference. In section 1, VAB1, that is the potential difference between A and B, can be written as 1 by 2 pi epsilon QA. Now you see, as I already told, that double circuit line means that the two conductors are carrying similar charge or same current because they are in parallel. So I can write or assume that the charges are equal and the current being carried by them are equal. This conductor is also carrying QA charge and this is also carrying QA charge. So we will have to find the potential difference between A and B due to both charges. So let us write the equation. Let us take this charge first. For this charge, D2 is small d and D1 is its radius only. That's why I have written here D and R. Similarly, for this charge, D2 is G. This distance between first conductor and middle conductor is G, and distance of this diagonal is F. So similarly, this distance is also equal to G and this distance is also equal to F. So that's why D2 here is G and D1 is equal to F. Similarly, we will write for the QB charge. Now QB charge is on both conductor, this conductor as well as this conductor. Now let us write for this conductor first. QB natural log D2 by D1. For this conductor, D2 is equal to R only. That's why I have written R here. And D1 is equal to small d. That's what it is written here. Now let us come to this conductor, the second conductor which is carrying QB charge. For this conductor, for this conductor, D2 is equal to this distance which is equal to H, which is same here, and D1 is equal to this distance which is G, which is written here. Similarly for QC, that is charge QC. Now charge QC is on two conductors, this conductor as well as this conductor. Now let's write first for this charge. For this charge, D2, the distance between point 2 and charge is small d. So it is written here small d. And D1, that is distance between charge and the point 1 is 2d. So it is written 2d here. Now let us see for this charge. For this charge, D2 is equal to the distance between charge and point 2 is G, which is written here, and D1 is equal to just H. It is written here. Similarly, I can write the potential difference between A and B during the section 2 or in this section once we transpose this. So using the same argument, I have written the equation for VAB2 here, which is equal to 1 by 2 pi epsilon QA natural log D by R plus natural log G by H plus QB natural log R by D plus natural log F by G plus QC natural log 2D by D plus natural log H by G. Similarly, in the third section, I can write VAB3 as using this similar argument as like this. Now, we will assume that the actual potential difference to cancel out any dissimilarity, we will take average of this and we will assume that this is the actual VAB voltage, that is average of VAB1, VAB2 and VAB3 will give me the actual VAB voltage. So adding these three equations, first equation, second equation and third equation, it will give us 1 by, and taking its average 3 will come here, that is 1 by 2 pi epsilon naught will convert into 1 by 6 pi epsilon. This 3 will multiply here na, and I will take QA terms common, QB term common and QC term common. We will see all the terms for QC will cancel out and only natural log 1 will remain and its value is equal to, this is equal to 0. Similarly, I will write the equation for VAC. We have just to change B by C. That's what I have done here. Now, as we already seen that VAB plus VAC is equal to 3 times of VAN. So, I will put this whole sum equal to 3 times of VAN. On solving, this will come out to be 3 by 6 pi epsilon QA natural log 2 dq by r cube into G square by F square. Now this 3 will cancel out. So 1 by 6 pi epsilon will remain. So VAN is equal to 1 by 6 pi epsilon QA natural log 2 d cube by r cube G by F whole square. Now if I take the cube common outside, so this power will become 1 by 3 and this total cube will become power 1 and this 2 will become 2 by 3 and 3 will come outside and it will cancel this 6, leaving only 2 here. Okay, in this way I can write this as 1 by 2 pi epsilon natural log 2 raised to power 1 by 3 d by r into G by F raised to power 2 by 3. Now the capacitance of this conductor which is carrying charge QA per unit length can be found out just by dividing QA by VAN, which will give me this value, 2 pi epsilon divided by natural log 2 raised to power 1 by 3 d by r G by F raised to power 2 by 3 farad per meter. But you see, as I already told in the previous video also, that this is just a capacitance between this one conductor and the neutral, but this phase is having one more conductor and these are in parallel, so their capacitances will add, giving us 2 times of this, that is 2 times of this will give me 4 pi epsilon natural log 2 raised to power 1 by 3 d by r G by F raised to power 2 by 3 farad per meter. Now we have seen the derivation by using basic concepts. Now let us see, can we use the modified GMD method here to find the capacitance of this configuration? Now let us see in the next slide. Now let's see the derivation using modified GMD method. Here, as we already know, that capacitance of phase to neutral by modified GMD method is given by 2 pi epsilon natural log D equivalent by DSC, which is the modified GMR of the conductor, farad per meter. Now we will find D equivalent in section 1. In D equivalent is written as DAB, DBC, DCA raised to power 1 by 3. But DAB is itself composed of 2 conductors, so we will have to write equivalent DAB using the GMD method. So DAB can be written as DAB, DAB dash, DA dash B and DA dash B dash raised to power 1 by 4. Putting their values, let us see DAB. DAB is D, DAB dash is G and D A dash B. D A dash B. A dash B is again G and D A dash B dash. A dash B dash is again D. which will give me root of GD. Similarly, DBC can be written as under root of GD, and DCA can also be written as under root of 2DH. Now, as a homework, you can do one thing, that you can verify the value of D equivalent in section 2 and section 3 also. You will find that D equivalent in section 1, 2, 3 are equal. That is, if I put the value of DAB, DBC, DCA in this formula, I will get the D equivalent value same in both three sections. So D equivalent for total all the section can be written as D equivalent in first section, D equivalent in second section, D equivalent in third section, raised to power 1 by 3. Since these are equal, so this raised to power 3 will get cancelled and it will give me only D equivalent 1. Okay. So it is not required to calculate D equivalent for all the section. Now let us come to the DSC. Now DSC will be different for all the three sections. So DSC in position 1, that is here in section 1, can be written as D. What is DSC? Let us say for phase A, we want to write DSC for phase A. It can be written as DAA, DAA dash, DA dash A, DA dash A dash raised to power 1 by 4. It is R, DA is R, DA dash is F, DA dash A will be F, and it will be R raised to power 1 by 4, which I have written here. FR raised to power 1 by 4, which will give me value under root of RF. Similarly, I can write DSC for position 2 also for phase A conductors, which will come out to be RH, and for position 3 it will come out to be RF. So DSC equivalent by combining all the three sections can be written as DSC in first section into DSC into second section and DSC into section third raised to power 1 by 3. That is DSC in section 1, DSC in section 2, DSC in section 3 raised to power 1 by 3, which will come out to be this value. Now if I put these D equivalent and DSC equivalent in this formula, I will get the capacitance of phase to neutral, that is capacitance of this full phase A, as 4 pi epsilon upon natural log 2 raised to power 1 by 3 D by R into G by F raised to power 2 by 3, which is same as the equation which we got earlier using the basic concepts. So this shows that modified GMD method can be utilized for calculating the capacitance of a double circuit line also. In this way, we have generalized this concept that modified GMD method is equally applicable for the calculation of capacitance of various types of configuration. At least we are sure that if the configuration lies between a hexagon and a vertical or flat spacing, then the modified GMD method is 100% applicable. And this also builds up our faith on modified GMD method, and it is it is sure that it will work for all such configuration. So instead of using the basic formula or basic concepts every time, we will have to just remember this formula: C phase to neutral is equal to 2 pi epsilon natural log D equivalent by DSC, and we should know how to calculate D equivalent and DSC. These are very simple. We need to just know how to calculate GMD and GMR of a conductor, of which we have done several examples while we calculated inductance. Also, we will do some example for the calculation of capacitance of various configuration in our next videos. Now, if you find my lectures helpful, then it is requested that you please subscribe and share my channel. And we have also created a Telegram channel whose link is given in the description of this video. So if you want to join that channel for doubt discussion of the topics which have been covered on the online lectures, then you should join that channel. Thank you.